Okay, so we're going to now work on lesson 4.2, which is limits and continuity. All right, so there's actually a lot more note-taking in this one than there is necessarily in examples. There aren't that many examples. Luckily, we do have 2 extra slides to play with if we need them. So let's dive into it. So 4.2, limits and continuity. Learning objectives. Calculate the limit of a function for 2 variables. Learn how a function of 2 variables can approach different values at a boundary point depending on the path of the approach. State the conditions of continuity of a function of 2 variables. Verify the continuity of a function of 2 variables at a point. And calculate the limit of a function of 3 or more variables and verify the continuity of the function at a point. And then we have our definition here. If we let f of x be defined for all x not equal to a in an open interval containing a, let L be a real number, then we would find the limit as x approaches a of f of x is equal to L. For every element greater than 0, there exists what is that Greek word? I'm gonna have to look it up. Okay, so I pulled up a Greek alphabet. I can never remember this guy. Oh, it's little delta. That would be why. Don't know why they couldn't just use the one I'm used to. All right, such that if 0 and delta are the range for the absolute value of x minus a for all x in the domain of f, then the absolute value of f of x minus L would be less than epsilon. I think before I called that the element, because that's what it looks like. All right, well, you got that. Before we can adapt this definition to define a limit of a function of 2 variables, we first need to see how to extend the idea of an open interval in 1 variable to an open interval in 2 variables. So definition, consider a point AB is an element within R squared. A delta disk centered at point AB is defined to be an open disk of radius delta centered at point AB that is the following as shown in the graph. Okay, so that is everything for the first slide. Like I said, it's just going to be a lot of definitions. So the idea, I think did I just make that bigger? No, it continues. So this idea that the alpha disk appears in the definition of the limit of 2 variables, if alpha is small, then all the points x, y in the alpha disk are close to AB. This is completely analogous to x being close to a in the definition of a limit of a function of 1 variable. If in 1 dimension, we express this restriction as the following. In more than 1 dimension, we use the alpha disk. So here's our definition. Let f be a function of 2 variables, x and y. The limit of fxy as xy approaches AB is L, written as the following. So you would want to write this down. If for each epsilon greater than 0, there exists a small enough delta greater than 0 such that for all points xy in the alpha disk around AB, except possibly for AB itself, the value of fxy is no more than epsilon away from L. Using symbols, we write the following. So is also important. Yeah, we don't have an example until slide 6. So, okay, so this kind of gives you an idea of what this image kind of looks like. You move it over a little so you can see all of it. Proving that a limit exists using the definition of a limit of a function of two variables can be challenging. Instead, we use the following theorem, which gives us a shortcut to finding limits. The formulas in this theorem are an extension of the formulas in the limit laws theorem in the limit laws section. Probably leads you back to that if you clicked on that hyperlink. There are a lot in this theorem, I'm pretty sure. It goes on to the next page. It does. So we have limit laws of functions of two variables. So we have the constant law. So if it's the limit of a constant, then that is going to be equal to the constant. If the limit is approaching x, then the answer is going to be a. If the limit is approaching y, then the answer is going to be b. We have the sum law, so it's going to be L plus M. We have a difference law, L minus M. Constant multiplier will be C times L. And again, you guys can pause the video so you can write all of these down, or you can get them from your textbook. They're also easily found there. Then we have the product law, so L times M. Quotient law, L over M, as long as M is not equal to 0. Power law, L to the N for any positive N, integer N, and root law. So that's going to be the L under the nth root for all L if N is odd and positive, and for L greater than or equal to 0 if N is even and positive, provided that f of x, y is greater than or equal to 0 for all x, y not equal to AB in the neighborhood of AB. Okay, like I said, again, I would obviously write down all of these laws. Oops. I'll put it there. Write down all of these laws with their names. Not saying that I might not give it to you, but it'll just be much better for your homework if you just have it all written down. Okay. All right, we are going to be doing, I believe, a part A and part B on two different slides. So the first one that we're looking at can be part A. It is actually very, 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 very lengthy, so we will try to get this all in one. So we want to do the limit of xy down here as it approaches 2, -1. And we're given x squared minus 2xy plus 3y squared minus 4x plus 3y minus 6. All right, so the first thing we're going to do is we're actually going to kind of split everything up. So we're going to say and rewrite the limit xy as it approaches to -1. And the first part's going to be the x squared, and then minus, and now it's the whole limit xy goes to -1 of 2xy plus, and you get the idea here. And as we keep going, then we're going to start pulling the stuff out too. But we'll write it each step for the first one. We won't combine any steps. 3y squared minus the limit xy to -1 of 4x, and then plus the limit xy to 2 negative 1 of 3y. And then you guys can see, at least for the last one, that's just going to be a constant. So we're going to be able to do that limit very quickly. Okay. All right. Next, we're going to use the constant multiple law on the second, third, fourth, and fifth limits. So that means we're going to pull out the constants and also do that last limit. They actually don't do it yet. They leave that part till the end. So I don't do everything. So we're going to rewrite the first one because there's nothing that can be pulled out. So that stays as x squared. Actually, they pull out the square. They put it on the outside. And then we'll pull the 2 out. Pull the 2 out, and we'll have the limit xy to 2 negative 1 x. And then we also will do it for the y. And if you guys paid attention to the theorem, you'll see why we're doing it this way. Okay, so then we'll pull the 3 out, and then we'll have the limit xy to negative 1 y, and then the squared will be pulled out. And then minus, and we're pulling out the 4, the limit xy to 2 negative 1. And then plus the 3 is pulled out. Limit xy to negative 1 y. And then they actually rewrite the limit again for this one, but I don't really have the room, so I'm just gonna go ahead with the minus 6. So we actually combined 2 laws here. We did the product, and then I also went ahead and did the power. So now we can use the identity laws on the first 6 limits and the constant law on the last limit, which I already did. I might be able to, here, I'll try to squeeze it in. So minus the limit, and it'll be a 6 x to y to negative 1. Okay, so now we'll have the limit. Keep trying to just do xy to negative 1 of x squared minus 2xy plus 3y squared minus 4x minus or plus 3y minus 6 is going to give us 2 squared, because we have to plug everything in now, right? So 2 squared minus 2 times 2 times negative 1 plus 3 times negative 1 squared minus 4 times 2 plus 3 times -1 minus 6. And if we keep working, we get 4 plus 4. Yeah, 2 times 2 is 4 times, and then -4 times -1 is 4. And then -1 squared is 1, so plus 3. Minus 8, minus 3, minus 6. So the 8's cancel, the 3's cancel, and we're left with a limit of -6. Okay. All right, so that's that part of that problem. All right, now we're going to work on part B, which is finding the limit as of xy as it goes to, again, to -1 of 2x plus 3y over 4x minus 3y. Not as many parts to this one. It's, it's not as long in a sense, because that first one was, really long. This is 2 division problems, basically. So we have the limit of 4x minus the limit of 3y. So we'll do the top, and then we'll do the bottom. And then we'll bring them together, which sounds like the best approach. So if we focus on just the top, we'll do the top in green. So it's going to be the limit of xy as it approaches to the 2, -1. And that's going to be just oh, sorry, we're doing the denominator first, because we need to make sure that it's not a 0. Otherwise, there wouldn't be a need to do the top. So 4x minus the limit dy, and then we can pull that apart. So we'll get 4 limit x to y to -1 x minus 3, the limit okay, so that's just going to end up working to be 4 times a and -3 times b. So you want to write that in there, like using the theorem, it would be 4 times a minus 3 times b, which would make that 4 times 2 minus 3 times b. And that gives us 8 plus 3, which is 11. So we have 11 as our denominator. We'll do our, we'll do it in red. So our numerator would be the limit x to y to -1 of 2 x. Let's try to do it a little bit, I guess, a little bit quicker. So we would have the 2 outside and the x on the inside, plus 3 on the outside, the limit x to y to -1, y is on the inside. So that's going to end up giving you 2 times a plus 3 times b, which is 2 times 2 plus 3 times -1 will give us 4 minus 3, so 1. So your overall answer is going to be 1 over 11. Okay. All right. So, part A for this one, show that neither of the following limits exist. So the first thing we want to look for is that the domain of the function f of xy, which is the 2xy over 3x squared plus y squared, consists of all points in the xy plane except for the point 0, 0. To show that the limit does not exist as xy approaches 0, 0, we note that it is impossible to satisfy the definition of a limit of a function of two variables because of the fact that the function takes different values along different lines passing through the point 0, 0. So first we want to consider the line y equals 0 in the xy plane by substituting y equals 0 into the function. So, sorry. Looking at part A. Fix yourself. Are you gonna make me? There we go. That's what I thought. So we're looking at part A. We're looking at the limit xy goes to 0, 0 for 2xy over 3x squared plus y squared. So if we sub in y equals 0, then we would get, so essentially we're doing f of x comma 0. We would get 2x times 0 over 3x squared plus 0 squared, which is going to zero out. Okay, for any value of x, therefore the value of f remains constant for any point on the x-axis, and as y approaches 0, the function remains fixed at 0. Next, we're going to consider what happens if we do x equal to 0, or f of 0 comma y. Then we would get 2 times 0 y over 3x squared, 3 times 0 squared plus y squared. Oh, oops. I apologize. We're actually plugging in. We're not plugging in for x. We're plugging y. We're plugging x in for y. So you would get f of xx, which is going to be 2x times x over 3x squared plus x squared, which would be 2x squared over 4x squared, which is just 1/2. So this is true for any point on the y equals x line. If we let x approach 0 while staying on this line, the value of the function remains fixed at 1/2. Regardless of how small x is. Choose a value epsilon that is less than 1/2, let's say 1/4. And no matter how small the disk we draw around 0, 0, the values of xy for the point inside the disk will include both 0 and 1/2. Therefore, the definition of the point is never satisfied and the limit fails to exist. So the definition of limit at a point is never satisfied, and the limit fails to exist. Okay, so I do want you to see this graphic. Okay, pull it down a little bit for you. Okay, so that's what that would look like. It kind of looks like if you took a tissue paper and you're pinching it kind of in that middle there. That's what that looks like. Okay. All right, so for this second one, this part B, it is a lot longer, so get ready for it. So we're going to do part B. We know that we have the limit x to y 0, 0 for 4xy squared over x squared plus 3y to the fourth. So in a similar fashion to part A, we can approach the origin along a straight line passing through the origin. If we try the x-axis, so in other words, if you put in 0 for y, then the function remains fixed at 0. The same is true for the y-axis. Suppose we approach the origin along a straight line of slope k. The equation for this line would be y equal to kx. The limit would become, so I already wrote the first part. And then we're going to equal that to the limit xy to 0, 0. And we're going to do, so right now we're considering y equals kx. Okay. So that would be 4x times kx squared over x squared plus 3 times kx to the fourth. So then if we go through and we want to work some stuff out, we'll get 4k squared x cubed over x squared plus 3k to the fourth x to the fourth. And now we can get rid of an x squared everywhere because it's in all pieces. So we would end up with the limit xy to 0, 0, which would be 4k squared over x over 1 plus 3k to the fourth x squared. And now at this point, we want to take the limits of the top and the bottom. So we'll have the limit x to y is 0, 0 for just 4k squared x. And then the limit x to y to 0, 0 of 1 plus 3k to the fourth x squared. It's 1 plus. So that's just going to give you a limit of 0. Okay, regardless of the value of k, it would seem that the limit is equal to 0. What if we choose a curve passing through the origin instead? For example, we can consider the parabola given by the equation, and I don't know if I'll have enough room on this slide, but we will try, x equal to y squared. Substituting y squared in place of x, we would have the following. So we will do the limit and we would have 4 y squared over y squared squared plus 3 y to the fourth. And then if we bring everything nice, we would get 4y to the fourth over y to the fourth plus 3y to the fourth. And then you can see that that everything is going to end up reducing to 1. So we would have 4y to the fourth over 4y to the fourth. So that becomes a 1. If you want, you can rewrite the limits there, but I mean, the limits at the end of it is still equal to 1. All right, by the same logic in A, it is impossible to find an alpha disk around the origin that satisfies the definition for any value of epsilon less than 1. Therefore, the limit does not exist. So, does not exist. It is impossible to find a delta disk around the origin that satisfies just not liking that word satisfies right now. Satisfies the definition of a limit. Limit for any value of epsilon less than 1. Okay. All right, so the next part is another definition. So let me see if I can move it in any way where you can see all of it. Not really. Okay, so interior points and boundary points. To study continuity and differentiability of a function of 2 or more variables, we must first need to learn some new technology. Definition: let S be a subset of R squared. A point PO is called an interior point of S where there is a delta disk centered around PO contained completely in S. At point P is called a boundary point of S if every delta disk centered around P sub 0 contains points both inside and outside of S. So you can see they have a good example shown there. All right. We have 3 definitions here. I'm just going to give you a few minutes to write those down. Okay. All right, hopefully you guys had enough time to write that down. If you didn't, you can always pause it, but we will keep moving. Okay, so limit of a function at a boundary point. Prove that the limit is equal to 0. So we have the domain, we have a graph of the domain of the function, we have the overall graph. So I'm gonna try and get you to there with enough room for writing everything out. Hopefully that happens. So the first thing you want to think about is the domain. So the domain of the function, we would do our rewritey thing that we've been doing. So I'm just gonna like go straight into it. So we would find that 25, right, minus x squared minus y squared would equal to 0. Or, it would 0 like that. And then we would switch everything around, move the 25 over. So it should be that, which should give us this overall answer for the definition, or the domain, sorry, not definition. All right. And that is going to look like this, which you guys definitely should have known or picked up that it would be a circle. So we can use the limit laws, which apply to the limits at the boundary of domains as well as the interior points. So now we need to look at the limit. So I'm not going to rewrite it. It's obviously right there for you guys. So what we'll do is we'll do the square root of the limit. Okay. And then we'll break it apart underneath. So we'll have the limit. Yeah, I don't know about you guys, but I'm just having such a hard time because you just wanted to go right away into drawing the arrow like you used to on 2 variables. So I keep like stutter writing, and I want to say like we're going to y, not like containing a y. Okay. So all those are there. And then what you're going to realize is that it's just going to end up being the square root of 25 because it's a constant minus the a squared minus the b squared. And if you use your theorems and all that, you should definitely be able to get that. So that would be the square root of 25 minus 16 minus 9. So that gives us a 0. And here is your overall image. Okay. All right. We are rolling. All right. The continuity of functions of 2 variables. In continuity, we defined the continuity of a function of 1 variable and saw how it relied on the limit of a function of 1 variable. In particular, 3 conditions are necessary for f of x to be continuous at a point x equal to a. First, the function of a has to exist. Second, the limit of f of x going to a has to exist. And third, the limit of f of x as it approaches x of a has to be equal to f of a. So these 3 conditions are necessary for continuity of a function of 2 variables as well. So again, we have a function f of xy. It is continuous at a point ab in its domain if the following conditions are satisfied. F of AB has to exist. The limit from xy to AB of f of xy has to exist. And then lastly, that limit has to equal f of AB. Okay, so let's look at an example of this. What we're going to do is we're going to go through the 3 steps, or the 3 conditions, I guess. So there are 3 conditions to be satisfied per the definition of continuity. In this example, a equals 5 and b equals -3. So if you weren't able to pick up on that, there they are. So the first question is, does f of AB exist? So condition 1, does f of AB exist? So that would basically mean, does f of 5, -3 exist? So we would just plug it in. I'll try to do it over here in the corner so we're not taking up a whole bunch of room. So that would be 3 times 5 plus 2 times -3 over 5 plus a -3 plus a 1. So that ends up being 15 minus 6 over 2 plus 1, which is 9 divided by 3, which is 3. So this first condition is satisfied. Let's do another color. Condition 2. And that condition is saying, does the limit as xy being 5 -3 of f xy exist? So we need to see, well, I guess if you're looking purely at a conceptualization level, this would be AB. So then we want to take the limit of 5 to -3 of 3x plus 2y over x plus y minus 1. And if we split it, what we end up finding out is, even though we write everything out, which means you would put the limit on the top and bottom, so the limit of 3x plus 2y on top, then you would rewrite the limit for the bottom. You will actually find out that is also equal to our 15 minus 6 over 2 plus 1, which is our 9 over 3, which is 3. Okay, so because conditions 1 and 2 are met, condition 3 states that the limit, so does the limit of f of xy, does it equal f of AB? And the answer for this case is yes. 3 equals 3. This is true because we have just shown it for both sides of this equation equal to 3. So, yes, f of xy as continuity at 5, -3. Okay. All right. So we have some more theorems. I'm going to move this one over. I was hoping to get it so you could see everything. I think you can see it. You can tell the bottom cut off, but it should be fine. So theorem 4.2, the sum of continuous functions is continuous If f of xy is continuous at x sub 0, y sub 0, and g of xy is continuous at x sub 0, y sub 0, then f of xy plus g of xy is continuous at the same point. The product of continuous functions is continuous. You can read that one for yourselves. And then lastly, the composition of continuous functions is continuous. Let g be a function of two variables from a domain to the range. Suppose g is continuous at the same point as an element of D and defines z sub 0 as g of x sub 0, y sub 0. Let f be a function that maps R to R such that z sub 0 is the domain of f. Last, assume f is continuous at z sub 0. Then f of g is continuous at the same point as the following figures would suggest to you. Okay. Very close to being done. Okay. I think this is like our second to last example. So, more examples of continuity of a function of two variables. Show that the functions f of xy and g of xy are continuous everywhere. So the polynomials all right, so if we look at it this way, the polynomials of g of x equal to 4x cubed, just kind of stay with me for a minute, and h of y squared are continuous at every real number, and therefore by the product of continuous functions theorem, f of xy, so these are continuous, so by the theorem, we know that f of xy equal 4x cubed y squared is continuous. All right. At every point xy in the xy plane. And therefore we also know that g of x equal to cosine of x is continuous. At every real number x. So then that tells us that g of x equal to, g of xy equal to the cosine of 4x cubed y squared is continuous at every point in the xy plane. Keep trying to map x on y, it's wrong, xy plane. So this one was more having to connect things and less like pure math of writing stuff down. It's more abstract thought, really. So, okay. All right, so one more definition and one more example, and we are done until Tuesday, though I do recommend you watch videos and do your homework between now and then. All right, so the definition says if we let x sub 0, y sub 0, z sub 0 be a point in R cubed, then a delta ball in 3 dimensions consists of all points in R3 laying at the distance of less than delta from that point. That is given the following domain. And then we take it a step further, and we have a point in 4 dimensions. The delta ball around P can be described as following. So we're going to look at an example with that. So I would definitely understand what this and this mean. Okay, so let me make this just a little bit bigger so you can see it. All right, so before we can apply the quotient law, we need to verify that the limit of the denominator is a non-zero using the difference law, the identity law, and the constant law. Okay, so first thing we have to check is the denominator. Okay, not 0. So we want to take the limit. We want to take the limit of x, y, z to 4, 1, negative 3 of 2x plus 5y minus z. So we're going to break everything apart like we did before. There are certain things that I just hate writing on the tablet. And eyes are definitely one of them. Oops, forgot to bring the 5 out. I wonder if I can there. Should have enough room now. The limit. All right. And then minus the limit. Okay. So we know, remember that if you have the limit of x, the limit of y, and the limit of z, it'll be those constants related to the other point. So we can just very quickly do this now as 2 times 4 minus 5 times 1 minus 1 times a negative 3. So that's going to give us 8 minus 5 plus 3. Oh, this is a plus. That's a plus. So that'll give us a 16. So that is not a 0, therefore we can keep going. Since this is a non-zero, we next find the limit of the numerator using the product law, difference law, constant multiple law, and identity law. Okay, so, all right. Looking at the numerator now, so our limit x, y, z goes to 4, 1, negative 3, and it's going to be x, but we're going to pull the squared out, and then times that limit repeated y. Then it'll be a minus 3. And then the limit z. So that is actually going to, again, we'll have that easier, quick identities. So it's going to be 4 squared times 1 minus 3 times negative 3, which is going to give us 16 plus 9. So that's a 25. So then if you bring everything together, applying the quotient rule, then, and I'm not going to rewrite it, you're basically going to get the limit for x, y, z going to 4, 1, negative 3 of this whole thing. Way too far over, sorry. X squared y minus 3z over 2x plus 5y minus z is going to just be 25 over 16. Okay. And that is it for this these 2 lessons. Sorry I had to split them up because of the Penn State game, but it was well worth watching the win. So if you need anything in the time being, you can always email me, but other than that, I will see you all on Tuesday for our regularly scheduled